For our preamplifier, we are using the AD620 instrumentation amplifier. AD620 is ideal for amplifying low-level signal with high accuracy. To set it up, connect the negative input signal to the inverting input pin 2, the positive input signal to the non-inverting input pin 3, and pin 5 connected to the ground. Then ensure the power supply pins are properly connected, where pin 7 to the positive voltage and pin 4 to the negative voltage. Next, the gain of AD620 is determined by the gain resistor RG and calculated using the formula found in the datasheet. For this project, we want a gain of 5. By using the formula, we choose 12 kilo ohm resistor and connect it between pin 1 and 8. Before cascading with other circuit, we simulate the preamplifier circuit to test it first and obtain V out and V in, resulting in experimental gain of 5.31. There is approximately 6.2% gain error due to resistor clearance and the absence of an exact 2.35 kilo ohm resistor. Finally, after testing, connect the output from pin 6 to the next stage of our circuit.
Okay, so for the second order high pass filter, the diagram that we did at the lab is shown as over here, and below the circuit diagram, that's the output, and the output that we get, the sine wave that we get for our high pass second order high pass filter. Um, Okay, so in the calculation itself, I've the frequency, the cutoff frequency is 3 hertz, and the resistor 1 and resistor 2 is 1 mega ohms. So from the calculation, the capacitance that we gain is 0.0531 microfarad, which is approximately 0.056 microfarad. For configuration, we are assuming it has the Butterworth characteristic. For for Butterworth response, we know that R A1 is divided with RB1 is equals to 0.586 with negative 40 dB. So the reason why it's negative 40 dB is because it's second order. And then the voltage gain for that we get from the theoretical calculation for second order high pass filter is 1.586. Based on the constructed result, the VP peak of channel 1 is 240 millivolts, and for channel 2 the V out is 384 millivolts. So whenever we divide V out with V in, the gain that we get is 1.6 the gain is 1.6, so experimentally. So if we compare the theoretical and the experimental gain, it's approximately same.
A second-order low-pass filter is a circuit designed to allow signals below the cutoff frequency to pass through while rejecting signals above that frequency. We'll focus on the Salem-Key design with Butterworth characteristics, which is known for its flat response in the passband. To achieve a specific cutoff frequency, we calculated the resistor and capacitor values. In our project, to target a 150 Hz cutoff frequency with equal resistor and capacitor values, each resistor is found to be 33 kilo ohms and each capacitor is 0.032 microfarad. The Salem-Key with Butterworth uses specific resistor ratios to set the gain, typically around 1.6. For example, with RA2 at 120 kilo ohms, RB2 would be around 200 kilo ohms, resulting in a theoretical gain of 1.586. In our real circuit, component tolerances can cause slight variations from theoretical calculations. The circuit have a slightly different RB2 value. Therefore, as we can see, the experimental gain of 1.519 is very close to the theoretical gain of 1.586. This demonstrates the effectiveness of the design process for the second-order low-pass filter. Even though there may be slight variations due to unexpected circumstances, the filter performs as we expected.
So this is our cascaded circuit with combining the AD620 preamplifier with the high pass filter and the low pass filter. The ECG conditioning circuit has successfully amplified the weak signal and filtered out the unwanted signal. The top left picture shows that the overall circuit configuration, and the top right picture shows the output at the 70 Hz. So the theoretical gain of the cascaded circuit is 12.6, where what we found actually in our circuit is 10.26. So there is 18.6% of the error comparing the actual and expected result. I'm going to explain the working principle of this circuit. So at 1 Hz, the output voltage is less than the input voltage. This means that the gain is less than 1. So I'm going to change the frequency to 20 Hz, and the output voltage is way higher than the input voltage, which is 32 volts. So the gain of this circuit at 20 Hz is 10. And now I'm going to change the frequency into 200 Hz, and the output voltage is 14.8 volts, and it started to drop already compared to the 20 Hz. So now when the frequency is at the 400 Hz, the output is similar to the input, and then the gain is nearly equals to 1. So now when the frequency is at 500 Hz, the output is lesser than the input, the gain is lesser than 1. Therefore, this is how the ECG circuit works.